Hi, this is Curtis Brown, and I'm from Texas Instruments. And I'm here today with Esther Brunat, and we are putting together a series of Smart Space videos. And this is Smart Space Video, Algebra 2, Review of Transformation of Functions. So Esther, if you want to go ahead and take it away, I'll let you go with it.
Yes, hello, TI family. So we are going to start off with a review of transformations of functions today. And just at the beginning of our video, just so we're not all over the place, I definitely like to just focus on quadratics, right? So that's our parent function, which is y equals x squared. And then this is our transformations. We're going to talk about each individually. We're going to talk about the plus and the minus. We'll talk about the a, we'll talk about the h, and then we'll talk about the k. So the first thing that I always like to talk about is what is that plus or minus about, right? So if I have my parent function, which is x squared, this is the table of the parent function, right? And when I plot those points, I have my beautiful parabola. And what is happening to the graph when I add just that negative right there in front of x squared, right? Well, I'm going to move each of these points. And what's happening now is what, Curtis?
It looks like you're getting the negative y value or the negative function value for each of those x values that you had in there. And it looks like my parabola just flipped upside down.
I like it. That's exactly what I'm looking for, right? So these are our new values. So when we look at one table versus the other table, we can see that in the f of x column and the g of x column, what happens? They turned negative. So that is called a reflection across the x-axis. Yes. So that's the plus and the minus in a nutshell, right?
Right.
So let's move on to the h value. I skipped the a. We'll get back there, I promise.
I was a little worried.
So same parent function. I always have my students repeat the parent function back to me because I want them to know it like the back of their hands. So same parent function. And when I just add a little x minus and then a 4 in there, I'm going to notice that my graph is going to do this.
Hold up.
Kurt, hold up.
So when you put in x minus 4, it looks like all of your function values like transition to the right 4 units. So does that mean that this h value affects the horizontal, it looks like?
Absolutely. It's a perfect answer. Look at you. It's like you knew this already. Great. So now I'm going to do something similar. And I'm going to do in my y3, it's going to be x plus 6. So based on what we just saw, what do we think this one is going to do?
So based on what you just showed me a second ago, it looks like what I'm trying to do is figure out how my original function values could kind of come back and equate the same. So if I take x plus 6, I'm going to need to like subtract 6 to get back to what that original horizontal value would have been. So I'm going to say that they're probably going to shift left 6 units.
Wow, brilliant. So I'm going to take these points from the original, and that's exactly what's going to happen. They're all going to shift. Yes. Gold star for you. And then this is what my table looks like. So what are we noticing about our table, Curtis? But from the parent graph to these new tables, what values are changing in the tables?
So I noticed that you've got all horizontal values that are changing, right? So in our original table, it looks like we have -2 to +2. And then in the g of x, or sorry, the y2, here you have from 2 to 6, right? So we shifted to the right 4 units. And then from our third one, y3, it looks like we've shifted left 6 units so that we went from -8 to -4 instead of -2 to to positive 2. So all the x values seem to be changing, but I noticed something. All the y values, they seem to be staying the same.
They're exactly the same. We love that because we're just messing with our horizontal shift right now. So that's what our h value do. That is a horizontal shift. Okay, let's move on to K.
Oh, yes.
Okay, so again, parent function. Same old, same old.
Gotta love that.
Swoop. So I have y2 is going to be x squared plus, I can't even see.
Nice.
2, 3. Okay, great. So all of those points shifted. Which direction?
3 units.
They look 3 units. I love it.
Units. Now, can I guess? All right. Looking at that, and I see my parent function, and I see I'm adding 3 to it. So that means that all of my y values, even before you did that, I could see that all of my y values were going to be 3 greater than what they were in that original parent function. Because effectively, I have the parent function plus 3.
Right. Look at that. That 4 turned into a 7. That 1 turned into a 4. The 0 turned into a 3. The 1 turned into a 4. The 4 turned into a 7. Plus 3.
Nice.
So at this point, we should be catching the hang of it, right? So for this next graph, I should be able to predict what it's going to look like on the coordinate plane, and I should be able to predict what the table is going to look like just by looking at the equation at this point.
Yep.
So these are my parent function points. What's going to happen?
So based on what we've seen so far, I'm guessing that every y value is going to shift down. All my x values are going to stay the same. So I should have something like a parabola that is shifted down 2 units that goes from -2 to +2 in the x direction. All my 2, -1, 0, 1, 2. And then my y values are now going to be 2, -1, -2, -1, and +2 again.
Oh my goodness. A star student, ladies and gentlemen. Perfect.
That was arithmetic in my head, by the way, which is really scary for me.
Listen, like mental math is not my strength, so I admire that. The K value moves the graph up and down. So great. That is my vertical movement on the graph right there. Fantastic. So we did the plus and the minus, we did the H, and we did the K. So what's coming next?
Looks like we're up to A next.
Great. So A is a little funny. It's not as easy. It's still great. Not as easy, intuitive as the others. So I'm actually going to use the TI-Smart view to do this because this visual on the calculator I think is better than my PowerPoint animations. So I'm going to go ahead and get my calculator.
Nice.
And we're going to go into our y equals screen, and we're going to put in all 3 functions, but we're going to do them one at a time. So first is our parent function. I'm going to reset my window to Zoom standard here so that everything's on the same playing field. So
Zoom standard
once
is
I do
that -10 to 10?
Yes.
Okay.
And then so now I'll put in the y squared, or y2, excuse me, equals 2x squared. And we notice something about that. And really quickly, I'm going to put in to my y3, 0.5 x squared. And we're going to graph. Great. So this is Curtis's expertise. I'm going to let him share with us what exactly is happening here on the screen with our A values.
So first off, I love that you put these in color coordination so I can see my parent function is the blue one. And that's important for us to kind of recognize that, hey, we've got the blue parent function there. So what we're doing now is we're actually exploring a dilation of this parabola. You guys might remember that from your geometry courses last year, talking about dilations of shapes. Yeah, you remember that? Okay, so what happened when you multiplied a shape by a value 2, when you dilated by a factor 2? What happened was the shape got larger, right? It got bigger. So what's happening here in our problem is we're actually taking this value, we're taking the parabola, and it's actually getting taller by a factor of 2 within the same viewing window, right? Well, what happens whenever we see that is our graph actually, if we look at y2, the red one here in the picture, the red one looks or appears to be narrower. Well, that's because of our viewing window. Our viewing window hasn't changed at all. We're still looking at this from -10 to +10. So we haven't changed the scale at all. So what it looks like is that when I multiply by a value of 2, my graph actually gets from sort of wide like this. I'm going to put my arms up like this and do this in the camera. And then when we multiply by 2, we get a little bit more narrow, right? It gets a little bit narrower. But that's because each of our function values actually got taller by a factor of 2. We multiplied each of those by a factor of 2. So we almost took this, and I've heard it called a stretch, right? We took the parabola and stretched it. The second thing that we've done now, if we look at the third one, y3, we actually take this same function, that y equals x squared, and now we're going to multiply it by a factor of 1/2. So we're starting here, we're going to take each of those function values and we're going to divide them by 2. We're going to shrink them down. We're going to divide them by 2. So they're going to get smaller. And what happens is they get smaller. They're still connected, right? It's still a continuous function. And so the graph actually appears to get wider. Now, that reason is because of the viewing window. We have not changed our viewing window. And the cool thing is, Esther, we can actually take that viewing window and change it. So if I changed my viewing window and went from -5 to +5, I would actually see the graph of 2x squared appear to look like y equals x squared from this viewing window. And the same thing would be true if I actually multiplied and went from -20 to +20 for my half x squared and compared that to a picture of the parent function on -10 to 10, it would also look like the same function. But the reason is because of our viewing window.
Perfect. Loving it. Okay, so our A values determine our vertical scale change, right? So if they are greater than 1, what happens, Curtis, if they're greater than 1?
Looks like the parabola grows a lot faster.
Love it. And if they're less than 1?
It means the parabola grows a little bit slower.
Wonderful. I love it. So now that we've reviewed just doing quadratics, right? We've done the A, we've done the H, done the K, done the plus and the minus. We definitely want to talk about what does it look like for all the other parent functions, right? If we applied this knowledge. So we have quadratics, which we just did, but what about cubics? And what about square roots? And what about absolute value functions? So we're just going to do a couple of them. We're not going to do all of them. And we're going to, based on what we just learned, make assumptions about what the graph is going to do compared to its parent graph. So number one, first of all, Curtis, you have to tell me, this is a hard question. Are you ready?
I'm ready.
What type of function is this?
Looks like a really positive one, right?
Yeah, I like that.
Absolute, yeah, see, I got your joke. It's the absolute value function.
Yes, so this is the parent graph of an absolute value function. Notice that anytime I put a value in there, when it pops out, it's going to come out. It's going to come out positive in the parent graph, right? So we have a transformation that's on the screen. The transformation is y equals the absolute value of x minus 2. So based on what we just learned, when that minus 2 is inside, right? Is that going to be, I always ask my students, is that going to be an A value? Is that going to be an H value? Or is that going to be a K value?
So based on what the formation of that parabola that you were just showing me, the quadratic a minute ago, I'm going to say that this is definitely an H value.
Perfect. So based on that, we know that this H value is going to push everything to the right 2 spaces.
That's
so
right.
I'm going to take my points and each of them is going to push over 2 spaces.
You know what I love? What I'm seeing,
What?
the domain being shifted to the right 2 units, right? So if I take
Mm-hmm.
x minus 2 and I think about what I'm doing to the domain values, so I'm going to take each one of those x values that you're plugging in over there in that table, I'm shifting them to the right 2 to keep the same function values. So that means that
Mm-hmm.
positive 2 for the function value is going to be paired up with the value 0, right? When I input x is 0, I'm going to get out f of x is positive 2.
Wonderful. So we're going to get rid of that parent function, and we're going to look at our new transformation, the table. And exactly what Curtis said is true, right? So when we talk about our domain of the entire function, because there's arrows, it goes on forever and ever. We're not just talking about the 5 points that we decided to plot on the graph, right? It goes on forever and ever. So that domain is going to be all real numbers, right? But when we talk about our range is a little bit different. So I like to show a boundary, right? So our range doesn't go on forever and ever. Our range is going to be, it's going to stop at a certain point, but it's going to go up forever. Curtis, can you talk about that a little bit?
I can. So it's really kind of cool, the absolute value function. So when we talk about absolute value, you may remember from way back in like 7th or 6th grade when you started talking about number lines and talking about absolute value as a measurement, as a distance, right? What we have going on here is we have now a function that is talking about distance, right? And so what we get to all those positive measurements, those positive distance values. So if I'm inputting a value -2 and I ask the question, how far is it from 0? I'm going to output the value +2 because really it is 2 units from 0. So that's why we have that boundary value there.
Love it. Wonderful. So that's a transformation, like in a nutshell. We decided our domain, decided our range, absolute value, boom. So really quickly, we'll do a square root function, right? So we have the parent graph of a square root function, and this 2 is not under the square root symbol, right? It's on the outside, okay? So it's on the outside. So this is what kind of value, Curtis?
Well, it looks like it's outside of my parent function, right? So parent function is x square root of x. So I'm guessing that this is a k value.
Perfect. So this is my parent function, which I'm graphing, and we already decided k values move it vertically, right? Either up or down. And in this case, I have a -2. So it's going to move each point down 2 spaces. Swoop. When I get rid of my parent function, great. So then this is my table. All I did was move each point down, right? So we got to talk about our domain and our range, just like last time. Is our domain going to be all real numbers this time, Curtis?
Well, it's a little bit difficult to take the square root of negative values. We get imaginary numbers and things get a little bit screwy. So I'm going to say that probably since we want to input real numbers, let's call the domain equal to 0 and greater, right? So it's not a real number.
Look, I'm telling you guys, it's like he knows. So if I show that boundary, our function starts right there at 0, and then it goes on forever and ever. So I get rid of that boundary. If I'm talking about my range, something very similar happens with our range. But because our function was moved down 2 spaces, that starts my range at a -2 value and then goes on forever and ever. So I'm going to say
We've
y is
taken
greater
the
than.
whole domain and subtracted 2, right? So
Exactly.
we started off going from 0 to positive infinity for the range, right? And now we're taking that entire range and translating it and sliding it down. And so now we've got the entire domain going from -2 to positive infinity. Love it.
There we go. We love it. Swoop, out of there. And then I just have a funny video of parent functions.
Yes. This is like all the parent functions at once.
That's exactly. So
That's
that
so
is
great.
definitely the conclusion. That is parent functions and transformations in a nutshell.
Fantastic. Well, thank you, Esther. It's so much fun teaching a lesson with you and talking through kind of a review of transformations of functions. Looking forward to some more lessons like this. We'll join you guys next time on another Smart Space video.